All right, so here we are on 10.5 on implicit differentiation. So we're going to look at special function notation as well as the actual implicit differentiation. Okay, so until now we've considered functions involving only one independent variable, usually x. And so now what we're going to do is we're going to say, okay, well, that was x is equal to 2t squared minus 3t plus 1, and that's our x of t. Or, we could have also z, which was the square root of u squared minus 3u, which was z of u. Or we could have r was 1 over the s squared minus 3s all to the 2/3 power, and that would be r of s. But now what we're going to do is we're going to kind of mix functions together. So we're going to borrow the notation for a function involving two independent variables. So for example, if we had f of xy, that would be, you could have something like x squared minus 2xy plus 3y squared minus 5, or, any combinations of x's and y's or z's and any of these letters. But what we're going to do basically, we're going to have a new function involving two independent variables. So let's consider the equation 3x squared plus y minus 2 is equal to 0. Now, the equation, we can have this and we can solve it for y. We can add 2 to that side, subtract 3x squared, and we get y equals 2 minus 3x squared. Now, both equations here define the same function with x as your independent variable, and that's going to be the key. Some of our problems we're going to look at, we're going to be changing x's and y's, and so, the y might be x and the x might be t, and so we're going to have to really follow what we're doing here. And so in this case, the x is independent variable and y is our dependent variable. And so basically then y is a function f of x. So we plug in some value x and we'll get our y value out. So we usually write that f of x equals 2 minus 3x squared. And we can explicitly state the rule that enables us to determine y for each value of x. So whatever we plug in for x, we plug it into here and we get a y value out. So it's an explicit rule. Now, on the other hand, the y in equation 2 all the way back up here, it's in the middle here. It's the same as the one where we solve for y in this equation 3 here. And it basically implicitly gives or implies, though it doesn't directly express y as a function of x. So we say that equations 3 and 4, the y equals 2 minus 3x squared and f of x equals 2 minus 3x squared, define the function f explicitly. And equation 2, which is our original one up here, that defines f implicitly. And so we're going to use an equation that defines the function implicitly to find the derivative of a function, and that's going to be called implicit differentiation. So it's a little bit different than what we've been used to. So when we perform implicit differentiation, since y is a function of x, but is not explicitly given, simply we write y prime is equal to d dx of y of x. So for example, if this is our equation, and really remember our original equation was 3x squared plus y minus 2 equals 0. And so we're saying, okay, now we're going to take the derivative of this. So we're going to say d dx of 3x squared. So we're putting a d dx there plus d dx of y of x. And now we're kind of saying, okay, well, we know y is a function of x. And so we're going to replace y with y of x and say d dx. And then minus d dx of 2 is equal to 0. Now we can take the derivative of this. Well, this is just going to be, bring that down. It's going to be 6x. Now this is equal to y prime, so we're going to call that y prime. And when you take a derivative of a number that's 0, and really, they didn't show it here, but there's also a d dx here, and the derivative of a 0 in this case is also a number, so it's also 0. Now, with this, we can solve for y. We just take our 6x to the other side, and we get y prime is equal to negative 6x. So would that be the same thing as what we did over here if we could do it? Well, if we took and found f prime of x directly, well, that's just going to be a minus 6x. So if we'd solve for y, we could get that directly. Explicit differentiation. Implicit differentiation, guess what? Eventually, we get the same thing, but we had to go through a little bit different steps. And the reason why we're going to do this is sometimes we're going to get equations that we can't solve easily for y, and therefore, this is really our easiest way to find the derivative. Okay, so let's stop there and we'll come back for an example.